All right, so now we have a situation where we have an output. It could be consumption or utility or production, a z value that's a function of at least two or more inputs. So we can think of z as the production of a company, x could be labor, and y could be capital, machines. So they're both inputs, factors of production. All right, so what we're going to do is take some partial derivatives. So what we do with partial derivatives is if we take the partial derivative of this function f of x with respect to x, what we do is we treat y as constant and just take a first derivative. So let's look at an example. So let's look at an example of utility that's going to be a function of expected return. And that should be a bar over an R, and a function of volatility. So this is the standard deviation of return. And so we're going to use a workhorse model in finance, the mean variance utility function. So what we have here is expected return minus 1/2 A times the variance, standard deviation squared. All right, so what we see here is that if we take the derivative, as expected return goes up, utility increases, and as volatility goes up, utility decreases. So this half right is just for convenience. All right, so let's take the derivative of the partial derivative. So we don't have a d, it's this little kind of delta thing. Partial derivative of utility with respect to expected return. And we see there's an implicit 1 in front of this. So it's just 1. And if we take the derivative of utility with respect to the volatility, and so what we do here is take the first derivative of that, cancels out with 1/2, and it's going to be negative A times the volatility. All right, so this conforms to our intuition. As risk goes up, our incremental amount of utility is negative, and as expected return goes up, our utility increases. All right, so that tells us some information there. And I guess we can see, let's say we have expected return here, and expected return on the y-axis, volatility on the x-axis. Well, what's the relationship between expected return and volatility? So there's probably a risk-return trade-off. Well, this is where we look at total derivatives. So the total derivative of where z is a function of two input variables x and y, the total derivative is going to be the partial a derivative of xz, I should say, with respect to x, holding y constant, times the change in x. And we have the change in z with respect to y holding x constant, times the changes in y's. So we can think about these as kind of like regression coefficients. You know, holding the other variables constant, this is the sensitivity of z with respect to x, and this is a sensitivity with z respect to y holding other variables constant, and here we change the variables. All right, so if we look at du, it's going to be the first derivative, the derivative of u with respect to the expected return times the change in expected return, plus the derivative of utility with respect to volatility times the change in volatility. And one thing we can do is we can set the change in u equal to 0. So what we're going to do is find indifference curves. Or iso-utility curves, sometimes, just make it singular. All right, so what we want is the relationship between dr and du. All right, so bring this over to the other side, do some algebra. And so what do we have here? We have the derivative of u with respect to, and these should be a little funky d's, with respect to volatility over du with respect to expected returns. All right, so before we had this as negative a sigma, and the derivative of u with respect to r is going to be 1. And so what we have is this relationship. So the slope when volatility is 0 starts off 0, but as volatility increases, the slope increases at an increasing rate. So we have this quadratic relationship. All right, so it turns out that every point along this red line gives you the same level of satisfaction. Right, and so let's see, this point right here we can sometimes refer to as the certainty equivalent return of a risky asset. So if we have A, B, we're indifferent between this volatility and that volatility, assuming they have these expected returns. And we're indifferent between A and B and a risk-free rate equal to, let's say, R0. Right? But if we have a second utility curve, every point along here, hey, it gives us a 0 risk but higher certainty equivalent return. So we prefer, with 0 risk, we prefer R1 over R0, because more return is better than less return. So every point along this blue line, C and D, are going to be better than any point along the red line. So ideally, what we want to get to is as north and west as we can get. And so we want the highest northwest portfolio we can achieve. So that's where we're going to go with partial derivatives. So that's enough for this topic.